Hello and welcome to Lecture 1 of the Acceleration Unit in Phys 1104. We've already seen an example of accelerated motion because we looked at a falling ball at the end of last unit, and that's an accelerated motion. But this whole unit is going to be about acceleration because it's one of the most important ideas in this whole course. One thing that gives students a bit of trouble when thinking about acceleration is that the way physicists use the word acceleration is different from the way it gets used in everyday speech. So in everyday conversation, when someone says that something is accelerating, they generally mean that it's speeding up. But that's not what a physicist means. To a physicist, an object is accelerating anytime its velocity is changing in any way. And there are several ways that velocity can change. One is that the object can be speeding up. And so this is the case where the physicist's definition agrees with the everyday definition. But if something is slowing down, its velocity is changing. And so a physicist would say that a slowing down object is also accelerating. And finally, here's an object that's moving at constant speed. But the direction of the velocity is changing, and so this object is also accelerating. There's nothing wrong with the everyday meaning of acceleration, but physicists use the word differently because it's more useful to use it that way. The reason comes down to something that we'll see later in the course, but it's that the causes of objects speeding up, slowing down, or changing direction of motion are all the same. And so since the causes are the same, we might as well give the same name to the effect. Let's think about a race car and a truck, both moving parallel to the x-axis and speeding up so that they start going 50 kilometers per hour and end going 100 kilometers per hour. And note my vector notation, the I hats here are just saying that these are velocities in the x direction. Well, for a race car, it's perfectly reasonable to think that it can go from 50 kilometers per hour to 100 kilometers per hour in 2 seconds, or in fact less, but let's say 2 seconds. The truck, though, depending on how heavily loaded it is, might take 20 seconds. So we can now talk about the accelerations. Now, both of them have changed velocity, and their changes in velocity are the same. Both have changed velocity by 50 kilometers per hour in the positive x direction. But the race car did it in far less time, and so we would say it has a higher rate of change of its velocity. So this is the average x component of the acceleration. We would take the change in the x component of velocity divided by the time it took for that change. And so this is a rate of change. For the race car, that gives us 25 kilometers per hour per second in the x direction. So on average, each second, it's speeding up by 25 kilometers per hour. Whereas for the truck, that's a much lower 2.5 kilometers per hour per second. And I just want to point out, these are averages because all we're working with is a final and initial velocity. We don't know when in this time period most of that change happened. Just think about the units for a moment. I used these units to make it clearer what the meaning of this acceleration is. Each second, the race car, on average, is speeding up by 25 kilometers per hour. Let's just convert that to more useful units for physics. First of all, I'm just going to rewrite it to make it clearer how those units are in a numerator and a denominator. And now I'm going to convert in the usual way using conversion fractions. And I get 6.9 meters per second squared, which actually for a race car is a pretty modest acceleration. So I just want to point out that these have different units, but their dimensions are the same. In both cases, the dimensions here are a length divided by time squared. Acceleration has direction associated with it, and so that makes it a vector. And let's see how we figure out which way the acceleration vector points. It's going to work the same way we've already seen. we just calculated average accelerations for single components, but more generally, just as we saw for average velocities, we're going to be able to define an average acceleration as a change in velocity vector divided by the time. And the time interval is only going to affect the size of the acceleration. It's not going to affect the direction. So if we just want to figure out the direction, we just need to find the direction of delta v. So let's do that. Suppose we have a race car and it's speeding up. Then, as usual, to get the delta v, we're going to take vf minus vi. So let's do that. We take our vf, we're going to take negative vi, and now we're going to put them head to tail to add them. And so our delta v has to point from where we started standing on one of these vectors to where we ended up if we walk head to tail on both of them. And so this vector I've just drawn is not actually the acceleration, it's the delta v, but it points in the same direction as the acceleration. And so we now know that this acceleration is pointing in the direction of motion. Now suppose instead the driver of the race car puts on the brakes and slows down. So we're going to do the same thing. We're going to take our vi, we're going to flip it around end to end to get negative vi. We're going to add that to vf by putting them head to tail. And now our delta v will point from where we started here to where we end up back here. And so we see that our delta v points back opposite to the direction of motion. And so we know that our acceleration, in this case where we're slowing down, points opposite to the direction of motion.
Let's check your understanding. So if you throw a ball straight up, you may note that as it moves upwards, it will slow down. You can certainly verify that in the lab. So a motion diagram would look like this diagram over here on the right. So which way does the ball's acceleration vector point during this motion? If you're doing this through Moodle, Moodle will now ask you this question. Otherwise, I think you should still answer the question for yourself before you go on to the next part of the lecture.